Okay, we're going to cover section 1.8. So this is all about absolute value. We're going to start out with the first example, which first example states if we have absolute value of 5 minus 3x equals 12, they'd like us to solve that. Part B we'll put down here a little bit further. Part B says, what about if we have 4x minus 3 is equal to x plus 6. So the idea is if this interior part here of the absolute value, if I can replace the whole 5x minus 3 with the 12, absolute value of 12 is 12, that'll make the equation true. Or if I can set the entire inside part there equal to negative 12, since absolute value of negative 12 is also 12, that will make the equation true. So what I'm going to do is set 5 minus 3x equal to positive 12. That'll get us one solution. Then I set 5 minus 3x equal to negative 12, and that will generate our other solution. So here I subtract 5 across. I get negative 3x equals 7. Here I subtract 5 across, and I get negative 3x equals negative 17. So to get x by itself here, I divide by negative 3. So it'll cancel. That'll say x is negative 7/3. Down here, I divide by negative 3. So that'll cancel. That'll say x equals negative over negative is positive. So I'll get positive 17/3. And these will be my two solutions. So if you get absolute value of expression dealing with x equals a positive number, you set the interior of the expression equal to the positive value of this, and then you set the interior of the expression equal to the negative of it. So part B is going to be dealt with in kind of a similar way. If we think about it, if the interior here, if we replace the interior here with a x plus 6, then this would be absolute value of x plus 6 equals itself, so the equation would be true. But since absolute value make negatives positive, if I replace it with a negative x plus 6, absolute value of the negative would peel the negative away, and we would be left with the same thing. So we kind of have the same idea here as we had in the previous one, where I set the inside of the first term equal to the second term as is, and I set the inside of the first term equal to the negative of the second term. So now I need to start solving for x. So I'll subtract x across, add the 3 on over. 4x, take away an x is 3x. 3x equals 9. We'll divide by 3. And I'll say x is 3. Over here, I let the negative distribute. I'll add the x across. So that'll give me a 5x equals, I'm going to add the 3 back across. Negative 6 plus 3 is negative 3. Divide the 5 on over, and I get x is negative 3/5. And that will solve those types. So basically just set the inside of the first absolute value equal to the inside of the second, then set the inside of the first equal to negative of the inside of the second. Should note, sometimes some of these equations don't solve. Sometimes you get one of them to solve and the other one will end up with something that doesn't make sense, like negative 3 is 5 or something like that. Sometimes they both don't work, but so just kind of be aware of that as you solve these. If you're getting one of them not working and the other one does, that's something that can happen with these. So for our next example here, we're going to take a look at solving the, kind of make up our own example here, kind of just do a different thing than is in the textbook. We're going to say like 3x minus 5. Where is that less than positive 7? So when you want to solve one of these where you're comparing the absolute value is less than a positive value here, what ends up happening is the inside of the absolute value gets stuck in between the negative of the number here and the positive of the number there. So we get negative 7 is less than or is less than 3x minus 5 is less than positive 7. So your goal here is to solve these for x, and in these we want to answer them in interval notation. So we're going to add 5 to all three places. It'll cancel here. That'll leave me a 3x in here. Negative 7 plus 5 is negative 2. And then 7 plus 5 is 12. I'm going to divide all three spots by 3. So that'll cancel there. We get negative 2/3 is less than x is less than 12 divided by 3 is 4. And to put this in interval notation, we're going to get open bracket negative 2/3 up to 4 open bracket. So the indicator that you're going to do this triple inequality is you see a less than or equals. If we had one with a less than or equals, something like that, the interior part, you just put or equals under the inequalities when you set it up initially. So basically the difference is if we had an or equal here, you would have put an or equal under your inequalities there, and they would have carried through with or equals on them. So we get this. Our goal is to get x by itself in the center, so I subtract 2 from all the places. I get negative 12 is less than or equal to negative x is less than or equal to 8. To divide everyone by negative 1, when I divide by a negative, the inequalities change direction. So I get 12 is greater than or equal to x is greater than or equal to negative 8. So when I go to write this in interval notation, negative 8 is a smaller number, so I go from negative 8 up to 12. It's okay to equal negative 8, so it gets a square bracket, and it's okay to equal 12, so it also gets a square bracket. And we just box that in. And that is how we handle those types. So the final case will be what happens when you have a greater than instead of a less than. So what if we had absolute value of 2x plus 3 is greater than 5? So what we do here is this is going to split into two cases. We get 2x plus 3 is greater than 5, or we get 2x plus 3 is less than negative 5. And the reason that it looks like that is if we looked at where does absolute value of stuff equal 5, it occurs at negative 5 and at positive 5. If you want your absolute value to be greater than negative 5, you need to be more negative than negative 5, which will be kind of out in this region, or you need to be more positive than positive 5, which is why we're getting this kind of splitting up into two cases. So this is showing where are we less than negative 5 would be kind of this arrow, and where are we greater than positive 5 would correspond to that arrow there. So then you solve these individually. So subtract 3, divide by 2. So I'm subtracting and dividing by positive numbers. My inequality doesn't change direction. Here subtract 3. Here divide by 2, dividing by positive, again, the inequality does not change direction. So I get x is less than negative 4. I'm going to list that one first because that's negative 4 down to negative infinity. Then I join it up with x greater than 1, so that's 1 up to positive infinity. And I have open brackets on the 1 and the negative 4 because these are not or equals. If we do one with or equals, it works kind of the same way as the previous types. You just put or equals into the expression. So where is that greater than or equal to 4? So we get negative 2x plus 1 is greater than or equal to 4, or negative 2x plus 1 is less than or equal to negative 4. So here we'll subtract 1, we'll get negative 2x is greater than or equal to 3. We'll divide by negative 2. This will flip the inequality. So we'll get x less than or equal to negative 3 halves. This side we subtract 1, we get negative 2x is less than or equal to negative 5. Divide by negative 2. Dividing by negative flips the inequality direction. So I get x is greater than or equal to positive 5 halves. So when I write this out, it's negative infinity up to negative 3 halves, union 5 halves up to infinity. And that will solve that one. So the next group, we got a couple of cases we're going to look at as to when you compare some stuff to negative numbers. So let's say I want to know, when is absolute value of x plus 3 equal to negative 5 for part A? When is absolute value of 3x minus 2 less than negative 6? And when is absolute value of 5x plus 1 greater than or equal to negative 2? If you remember, absolute value of stuff will always be positive or 0. So we're saying, when is something that's positive or when is something that's 0 equal to negative 5? Positive numbers never equal negative 5. 0 is never equal to negative 5, so this is no solution. Never is true. So here we say, when is this less than a negative 6? So we say, okay, well, absolute value is always positive or 0. Positive numbers are never less than negative 6. 0 is never less than negative 6. So here's another case where we have no solution. Down here, this is always positive or 0. When are positive numbers bigger than negative 2? That's always. When is 0 bigger than negative 2? 0 is always bigger than negative 2. So this will be true always. So the point is, when you compare to negative numbers out here, don't use the equations like we did up here when we were comparing them to positive numbers, or comparing them to positive numbers there, positive numbers there. Don't use your equations. If you're comparing them to negatives, you can kind of get it. Usually nothing works, or sometimes if it's a greater than, well, positives and 0 are always greater than negatives. So be careful when you compare, when you have the absolute value compared to a negative number by itself, because it'll, if you use the equations, you usually end up getting the stuff wrong. Okay, next statement. We're going to say absolute value of a minus b, or you could write it as absolute value of b minus a. Both these represent the distance between the 2 points. So that represents the distance between a and b. So for our example here, we want to write each statement using absolute value inequality. Okay, so part A says k is no less than 5 units from 8. And part B says n is within 0.001 unit of 6. Okay, so k is no less than 5 units from 8. We're talking about the distance k is away from 8. And then we have to kind of think about, what does it mean by no less than 5 units? Well, if you're not less than 5 units, you could be 5 units, or you could be greater than 5 units. So this is basically saying the distance between k and 8 is always bigger than or equal to 5 units, so it's never less than 5 units. So that'll be our answer to part A. Part B, n is within 0.001 unit of 6. So that means the distance between n and 6, if you're within 0.001 unit, that means you're always less than 0.001 unit. So that will be the distance between n and 6 is less than 0.001 unit. And then that means n is always within 0.01 unit of 6. So we're down to a final example from the section here. So we get example 6. They say suppose y equals 2x plus 1, and we want y to be within 0.01 unit of 4. For what values of x will this be true? Okay. So first we need to decipher what does it mean that y is within 0.01 unit of 4. So how we're going to do that, we're going to look at the distance between y and 4. And we're going to want that to be within, which means is less than 0.01 units. Now we need to figure out what x values will this be true. So we need something that gets us from y's over to x's, and what we're going to use is we're going to use that y equals 2x plus 1. So if I replace y with what y actually equals as 2x plus 1 minus 4 is less than 0.01, I get this expression here. I can simplify this a little bit more. Plus 1 minus 4 is minus 3. And then this is absolute value of something is less than a positive number, which means the interior of the absolute value goes here in the middle. We get that it's stuck between 0.01 and negative 0.01. So we're going to add 3 because our goal is to get the x by itself in the center. So 3 take away 0.01 would be 2.99 is less than 2x is less than 3.01 would be 3.01. We divide everyone by 2. Let's see, what is that? 2.99 cut in half. Sorry, negative 2.99 cut in half. No, it's positive. I guess we added 3. 3 plus negative 1 is that. So we get that's 1.495 is less than x. Then 3.01 cut in half will be 1.505. So if your x's are within the interval 1.495 up to 1.505, so x's in this region will keep y's within the 0.01. Okay, so that wraps up section 1.8.